Hello everyone and come back to my YouTube channel. My name is Anish Shah, CSCCY. The subject today is DDCO and the topic is KMAP. KMAP, Mastering Logical Circuit Design. This presentation will introduce the power of KMAPs, a valuable tool for simplifying and optimizing logical circuits. We'll explore the fundamental principles behind the KMAPs, learn how to construct and minimize them, and discuss their wide range applications in digital design. Introduction to K-maps. Visual logic representation. K-maps offer a visual way to represent and manipulate Boolean functions, making complex logic problems easier to grasp. Simplified logic design. K-maps enable the simplification of Boolean expressions, resulting in optimized circuits that use fewer gates and components. What is a K-map? Definition. A K-map is a graphical method for minimizing Boolean algebraic expressions. It represents truth tables in a visual grid format. Purpose. Simplifies complex logical functions by revealing logic relationships through spatial arrangement. Origin. Developed by Morse Carnot in 1953 as an improvement to Boolean algebra techniques. K-map theory. The K-map is a graphical tool used in digital logic design to simplify Boolean algebra expressions. It is named after Maurice Carnot, who introduced it in 1953 as an improvement over the vectoric diagram. The K-map minimizes logic functions, reducing the number of logic gates needed in a circuit. Structure of a K-map. Grid layout. A K-map is a grid-based representation of truth table. The number of cells corresponds to 2 to the power n, where n is the number of variables. Cell representation. Each cell represents a minterm, also known as the product term of the Boolean expression. The cells are labeled such that adjacent cells differ by only one variable's value. Gray code arrangement. Row and column labels. Row and column labels represent the possible combinations of the input variables. For example, in a three-variable K-map, the rows may represent combinations A and B, while in the columns represent C. Key concepts. Grouping. Adjacent cells with a value 111 logic high are grouped together to form simplified terms. Groups can include 1, 2, 4, 8, etc. cells, each with a power of 2. Simplification. Each group corresponds to a simplified product term in the sum of products (SOP) form. Similarly, for the product of sums (POS) form, groups of 000s are used. Overlapping and wrapping. Groups can overlap and the map wraps around horizontally and vertically. Don't care conditions. Cells marked as don't care XSX can be included in groups to achieve further simplification. Steps to simplify using K-map. Set up the K-map. Map the truth values 1, 0 or XSX into the corresponding K-map cells. Identify groups. Group all adjacent 111s or 000s for POS into rectangles or squares, maximizing the size of the groups. Derive the simplified expression. Write the Boolean expression for each group, omitting the variables that change within the group. Combine all group expressions into the final SOP or POS form. Example 3. Consider a Boolean function f abc sigma 1357. Map the minterms into the K-map ab/c 00011110. Group the adjacent ones. One group covers all c, which are equal to 1. Simplified expression f equal to b-c plus bc equals to c. Binary number system fundamentals. Base 2 system. The binary system uses only two digits 0 and 1 to represent numbers. Place values. Each digit in a binary numbers has a place value that's a power of 2. Conversion. Converting between decimal and binary numbers is essential for working with K-maps. K-map construction. Truth table. Start with a truth table that defines the Boolean function. Map grid. Create a grid with rows and columns labeled with binary values. Cell placement. Fill each cell with 1 or 0 based on the truth table row. Simplifying Boolean functions. Grouping adjacent cells. Identify groups of ones that are adjacent, either horizontal or vertical. Combining groups. Combine groups to create larger groups with powers of true. 2. Simplified expression. Write the simplified expression before the combined groups. K-map minimization techniques. Don't care. Utilize don't care conditions to further simplify the expression. Prime implicants. Identify and select essential prime implicants to ensure minimum logic. Minimized expression. The minimized expression leads to the most common cost-effective circuit. Identifying prime implicants. Grouping. Identify the largest possible groups of ones in the K-map. Selection. Choose minimum number of groups covering all ones. Optimization. Ensure each group represents the prime implicants. Applications of K-map. Digital circuit design. Optimize the logic of digital circuits, minimizing gates and reducing cost. Control systems. Simplify logic in control system, improving performance and reliability. Data processing. Optimize data processing algorithms, leading to faster and more efficient operations. Applications of K-map. Again, circuit design simplifies logic circuits by reducing the number of gates. Microprocessor design optimizes combinational logic in processors. Error detection helps in designing error detection correction circuits. State minimization simplifies state machines in digital systems. K-maps are a powerful intuitive tool, especially for up to 6 variables. For larger functions, automated tools like Quinn-McCluskey method or logic minimization software are often used. Complexity of large functions, variables, K-map complexity, and practical usability. K-map for 2 to 3 variables is very easy and is high practical usability, whereas K-map for 4 to 5 variables has very moderate complexity and good usability. But K-map for more than 6 variables are very extremely difficult and have limited practical usability. Disadvantages of K-map: limited scalability, becomes complex and widely with more than 4 to 5 variables. Manual process requires manual interpretation and careful grouping. Learning curve requires practice to master grouping techniques effectively. That's all for this video. I hope you understood K-map and thank you for joining me.